Hello everyone and welcome to this wonderful lecture. Today we're going to discuss on the subject digital image processing, and the topic that you're going to introduce for this lecture is on color image processing under the topic color fundamentals. My name is Dr. Victor Mokaya from the Department of CIT, Suresh Gyan University. Now today we are going to discuss on the topic of color fundamentals, and this is part of the larger domain of digital image processing, which will be narrowing down color processing, and we'll be looking at the color fundamentals. Now, these are the objectives that you're going to look at. The first objective that you're going to study is on grayscale and color image. We are going to find the distinction that exists between a grayscale image as well as a color image. Next, we are going to look at now the fundamentals of colors. We're going to look at the basic terminologies and the basic terms that are being used for colors. Next, we're going to discuss on the electromagnetic spectrum, and we are going to see how each of the spectrum appears or it is located within this spectrum. Next, we'll be discussing on the absorption of light, and here we'll be discussing more on the white light. Then we will be looking at the color gamut, that is the different color composition and color frequency exist. And lastly, we'll be discussing the quantities of light and color separation. These are the six objectives that you're going to do. After we cover these objectives in this lecture, we'll be able to attempt a quiz that you can brainstorm ourselves and recap on what you have already covered. Now let us get started. Now this first diagram that is shown to you, this is a diagram of a grayscale image. Now, if you can see clearly, the two different colors that we are able to see on this image are black and white. Hence, grayscale images are commonly referred to as black and white images. That is what is shown here. Now, this next diagram that is shown to you, this is the diagram of an colored image. So this is the same diagram that you've seen in the previous section, and now this image is now represented using all the color compositions. So we have three primary colors that are used to form the color image, and that is the red, green, and blue. When these colors are combined together, they form what is referred to as the color image. Hence, we have two types of colors, that is the grayscale image and the color image. One is the inverse of the other. Having said that, now let us come and discuss on the color fundamentals that exist. So whenever we are performing color image processing, then this color image processing is divided into the categories. First category that we do have color image. Now, remember, mark you here, we are discussing on color image. So we are not talking of grayscale, we're discussing on color. Hence, here we are talking of two types of categories. And the first category that we do have is the full image processing. Now, this full image processing basically obtained from a full color sensor, such as the one we can get from a colored TV or a camera or a colored scanner, sometimes from a colored printer. So these are the full color processing that we can get. So whenever we use this full color processing, it can be used for visualization of diagrams, graphs, and pictures. You can use it for publishing of content, okay? And also we can use it for internet usage, displaying of video and images. That is videographic content. Now, then other type of color processing category that we have is the pseudo color processing. Now, this pseudo color processing is basically used whenever we are dealing with objects that have one type of color, that is a monochrome intensity. So whenever we are having one type of color and then we want to introduce a different color scheme, then that color scheme that was not presently there and we want to introduce, that process is known as pseudo color. In this case, we use different range of intensities in order to perform the pseudo color. These are the two categories of color processing that. Moving further, now we have a brief history about color fundamentals, and this started in the year 1666 when scientist Sir Isaac Newton discovered that when a beam of light, that is white light, passes through a glass prism, then this beam of light is spread into a different spectrum of colors that range from red at one end and violet at the other end. Okay, so when this white light is dispersion, this process is known as dispersion of light. So whenever it is dispersed, it forms a range of colors that is from one end it's red and the other is violet. Okay, so this is what is referred to as now the color spectrum. So we also have the electromagnetic spectrum. Okay, so just before we come to the electromagnetic spectrum, let me remind you of something here. Whenever we are getting this color spectrum, we have this color spectrum labeled according to the size of each wavelength. How far each of these color can move or can be transferred. So we have the wavelength. Wavelength is the size, how much this color can be able to travel in light. That is what makes one end to be red and the other end to be violet. To be able to visualize how that these different wavelengths occur, we are going to use an electromagnetic spectrum to check that. So what happens that this electromagnetic spectrum is basically a range of frequencies. Okay, and these frequencies are of this range of represented in terms of nanometers. So nanometers are very, very small units that are used to represent distance. So these electromagnetic spectrum are of the range of electromagnetic radiation and their respective wavelength and the energy they possess. So we have those energies that are weak and we have those energies that are very, very strong. So we can say that these frequencies cover the range of 1 Hertz to 10 power 25 nanometer. So we can be able to divide this frequency up into different bands, and the electromagnetic waves from each band is given by different names. So we have one band that is referred to as the ultraviolet. We have the other one that is referred to as the X-rays. Another one is the infrared. We have the microwave. We have the radio waves. So for that case, all these bands are divided into two categories before we now divide them into their respective groups. That is, we have the lower frequencies and the higher frequencies. The lower frequencies are the radio waves, and they are those that are at the farthest right. So we have the radio waves, then followed by the microwaves, infrared, then we have the electromagnetic, that is the visible light, and then the ultraviolet. Those are the low frequency wavelengths or low frequency electromagnetic spectrum. So these ones they do not travel far, and also the energy they possess is very weak. We have the higher frequencies. Higher frequencies are known to travel further distances, and also the photon energy they possess is very high. So they are able to penetrate through matter and get into the substance. So in that case, we have two types, that is the X-rays and gamma. That's why you see that, like in microwaves, we know that microwaves can only be used within a given environment, and visible light is what you get it from the sun, and ultraviolet light is still what comes from the sun. But high frequencies such as X-rays and gamma, when you talk of the application, they are used in medical diagnostics. When you go to the hospital and you want a CT scan to be done to you or an X-ray scan, then they are going to use this high frequency band, that is the gamma rays and the X-rays. So they're able to penetrate through the skin, and they will be able to provide a pictorial representation of the internal body. So that is what these bands show. So each of them have their own characteristics. The lower band, the higher band have their own characteristics in terms of how they are produced, how they interact with matter, as well as their practical application. Each one of them is separate from the other, and they are not similar in any way. Okay, and that is why they are given different names. So in this case, this is the representation of each one of them. So we start from the gamma from one end, then come to the X-rays, then the UV, that's the ultraviolet, then we come to the infrared. Sorry, before we get to the infra, we have the visible spectrum of visible light. Then we have the infrared, we have the microwaves, then we have the radio waves. So this is the band, the different bands that we have, okay, and their distances and wavelength are. Now, next, what we are going to discuss is on quantities of light. Now, light is a very big subject, and we cannot be able to study it at one go or in a single class, because there are so many things to study and to learn from. And in that case, we are going to start from the basics. So when we talk of light, the opposite of light is basically darkness. Okay. So the first terminology we are going to look at is achromatic. Okay. Chroma is presence of light. So achromatic is the absence of light, while chromatic is the presence of light. So these are two terminologies that are opposite of the other. When you see achromatic, that means there's absence of light. When you see chromatic, then there's presence of light. So the chromatic light spans from the electromagnetic wavelength of 380 to 780. That means in the electromagnetic spectrum, where now we have visible light, is from the range of 380 up to 780. Okay, now if we check on this diagram, so light starts from somewhere here, 380, where now there's, you can see this range is showing some different colors. These different colors are due to the interaction white light. Okay. So this white light are dispersed up to 780. From this point forward, we don't see any color or light. That is referred to as achromatic. Okay, so now just a moment. Okay, so we have three basic quantities to describe quality of light. The first quantity that we use to describe quality of light is known as radiance. So radiance is the total amount of energy that flows from the light source, and it is usually measured using the units watts. So watts is what is used to measure radiance. The next we have is luminance. So luminance is measured in lumen. So luminance refers to the measure of the amount of energy an observer perceives from the light source. When you see an object, the amount of light that observer is able to receive or is able to view from his eyes is what is referred to as luminance. So, for example, light emitted from a source operating in the far infrared region of the spectrum would have significant energy that is referred to as radiance, but an observer will hardly perceive it. So its luminance will be almost zero. Okay. Next we have is brightness. So brightness is a subjective descriptor. Brightness is a subjective descriptor that is practically impossible to measure. We cannot be able to measure brightness. So it contains the achromatic notion of intensity and is one of the key factors in describing color succession. Okay. So next, we are going to discuss on the absorption of light. So the absorption of light can be represented using this graph. So along the y-axis, we have the absorption in arbitrary units. And on the x-axis, we have the distance that this light can spread. So represented in nanometers. The blue light, its absorption rate is 445 nanometers, and it can spread up to the length of 550. Whereas for the green light, its absorption rate is 535 nanometers. It can spread up to the length of above 650, but less than 700 nanometers. Lastly, we have the red light. Red light has the absorption of 575 nanometers, and it can spread up to the length of 700 nanometers. So when we now put this into perspective, along the blue spectrum, we have the bluish purple, then we have the purplish blue, then we have the blue, then blue green, we have the green, then yellowish green, yellow green, reddish orange, then red, as we move from the blue to the red color. So these are the different now color compositions that are formed as we increase the wavelength. Okay, so in simple, we can now define that absorption is basically the process of how objects take up the electromagnetic radiation and then convert this radiation into light. So as we move it, as the objects absorb this radiation measured in these nanometers, we see that at every point, different colors are formed because of the conversion of this radiation into light. Now we have sensors which are referred to as cones, and that is what is responsible for our eyes to see objects. So we have the human eye has cones of the range of 6 to 7 million and can be divided into 3 principal categories, that is red, green, and lastly, we have now the color fundamentals. So the color fundamentals are approximately 65% of all cones and are sensitive to red light. That 33% are sensitive to green light, only about 2% to blue. So this is how the cones are able to view the different color of the human eye. So that is 65 are sensitive to light. That is 65 out of 6 to 7 million cones that are present are sensitive to red light. Then 33% are sensitive to green light, while the remaining 2% are sensitive to blue. So we can say that the blue cones are most sensitive. Okay. So we have an international commission on illumination known as the CIE, and according to the CIE, the wavelength of blue are up to 435 nanometers, while the green starts from 541.6 nanometer, and the red color starts from the 700 nanometer. These are the different color fundamentals that we do have in existence. Next, we have the color formation. So color formation is due to the following mixture of colors. So we have different colors, like the basic colors that exist, we have is red, green, and blue. Now, whenever we have now different, like we've said, when we have the different absorption at the different wavelength, that is the distance of the electromagnetic radiation that is converted to white light, it forms these different colors. So as we move from the red towards now the green, where now the green and the red intersect, that radiation is converted into color. That color is referred to as the green. Where now the green combines with the blue, then that intersection between the green light and blue light is what is referred to as the Gyan color. While when the red and the blue intersect, that radiation that is converted to light is referred to as the magenta. Now, white light is now the composition of all the colors when they are formed together. So that is why whenever we say that this white light passes through a glass prism, then it forms, it is passed into 7 multiple colors. This is what forms the colors, the primary additive, red, green. Now we also have what is referred to as color subtraction. When we subtract these colors, that is, when we subtract what was formed when mixed, this white color was mixed with light, what do we have? So this is what we have. So we have the subtractive primaries. Now the primaries are now what was previously the intersection of these primary colors. So where we had the red, so when we combine magenta and yellow color, we form the red color. When we combine the magenta and the cyan color, we form the blue color. Lastly, when we combine the cyan and the yellow color, we form the green color. So all these colors are, when they are combined together, they form one primary color that is referred to as black. So black is a subtractive of the primary colors. So we can say that these are the primary colors that you do have, and these are the secondary colors that you have whenever we perform subtraction. This diagram has been extracted from General Electric Company lamp business. Now let us talk of color separation. So to be able to distinguish one color from the other, we use what is known, commonly refers to as brightness, hue, as well as saturation. Now brightness is the achromatic, that is the absence of color is known as achromatic. So is the achromatic notion of intensity. Okay. Then we have hue. Hue is an attribute that is associated with dominant wavelength, light wave. So we can represent hue as it is perceived by an observer. That is what is observed by somebody as red or orange or yellow. That is what is referred to as hue. That is why people will view an object. One will see an object as pink, another one will view it as maroon, and another one will view it as violet. That is referred to as hue, commonly referred to as colorblind. Then we have saturation. So saturation refers to the purity or the amount of white light mixed with. So that can be termed as the pure spectrum of colors, which are colors such as pink, lavender are less saturated, with the degree of saturation firstly of white light. These are the three components that are used for color separation. So now we're going to discuss on the two color separation components, that is hue and saturation, which are commonly referred to as chromaticity. So we can say that a color that is characterized by brightness and chromaticity, and that is referred to as tristimulus. So whenever we introduce this term tristimulus, we are basically referring to the three primary colors, that is the green, red, and blue. So we can denote this tristimulus using the variable x, y, and so the trichromatic coefficients are given as follows. So these were created by the CIE, as we've mentioned before. This is the Institution Commission of Illumination. That is x is given, the coefficient of x equal to x divided by x plus y plus z. The coefficient of y is given by y divided by y plus x plus z. And the coefficient of z is given by z divided by x plus y plus z. Hence, we can say that the value of the coefficient of x plus y plus z is equal to 1. Now we're going to look at the next, which is now the color fundamentals. And in this case, we are going to look at the chromaticity diagram. Okay. So in this chromaticity diagram is used to specify color according to their spectral energy. So we have the x-axis as well as the y-axis. So we start with the spectral energy, that is from now 380 up to 780. Okay, and then we look at its absorption rate. We are able to see different color. So we start with blue. Then blue, as the absorption increases, it rises up to deep. Okay. Now, where we have green, so as the absorption increases, so we are going on to have a deep green. Now, as we move further to the size of the wavelength, so we move up to yellow and then gold. So this is due to the interaction of now yellow as well as green color. It results in. So when we have white light, we can have a cool white, can have a warm white, as well as a daylight white. So at this point is where we refer to at point of equal energy. That is what is formed, and this is the result that obtained thereof. This is the chromaticity diagram that is used to refer to how the different, that is hue as well as saturation, are interacted with each other. So for any value of x and y, then the corresponding value of obtained by noting z is given by 1 minus x plus y. So that is, we can say that 65% of the values are given by green, 25% are red, and 13% are. So we can obtain pure colors at a boundary which are fully saturated. Okay. Whenever we are having full saturation of, say, green, red, and blue, that is the point where we are having the pure green. That is purest form of green and purest form of red as well as. And any point within the boundary represents a mixture of spectrum colors. And then we have equal energy and equal fractions of three primary colors present white, light. Next, the saturation point at the point of equal energy, normally 0. Now you can see in this diagram, the point of equal energy of this daylight and warm light where they are having equal saturation is known as the point of which is 0. So we use this chromaticity diagram whenever we want to perform color mixing. That is it. Next, we're going to look at color gamut. Okay. So color gamut is now what is used to produce different color channels, and it is basically used in it's sort of like RGB monitors, our televisions, our laptops, or any electronic device that has a display for color for RGB. So that is. So can you, in a typical color gamut, we have this triangle. This triangle is what is used to refer to different colors. So R refers to red, which is denoted at this position, and blue is found at this position because of its electromagnetic wavelength. That is why they are located at these points. And green is at this position. Okay. So these color gamuts will help us to know how to regulate different colors. Suppose we want to regulate more of green, then we know we'll have to move towards the 540 nanometer position. And similarly, when you want to move to the red color, we'll move to the 610 wavelength position. Similarly, for blue, we'll 450 wavelength position. So in this case, we can be able to know where we can apply this. For example, whenever we want to use the color gamut for RGB monitors, then they are produced in this location. And when we want to use the color gamut for high quality printing devices, then they are outside the triangle of the color RGB color gamut. So we can summarize and say that the color gamut is basically a complete subset of colors. The corners of the gamut are filled with the purest colors, that is green, red, and blue. For printing gamut is it has an irregular, but because it has an irregular gamut because color printing is a combination of both additive and subtractive colors. That is, white and black colors are added together so you can get this printing gamut. So this process is basically much more difficult to control than that of displaying the colors for a monitor. Because in monitor, we're just dealing with the additive color, but for the printing gamut, we use subtractive and additive color mixing. So this is based on the three primary colors. We have to regulate both the green, red, and blue in order to get the perfect printing gamut for printing, which is actually not available for RGB monitors. That is why you get a difficulty in regulating the color gamut for printing devices. Now we've come to the end of our lecture, and now we're going to perform a brief recap of what you have covered, and then we'll come back and execute the. So in the color fundamentals, we say that the color image, there are two types of colors, that is the grayscale color and the RGB color. Similarly, we've mentioned that we have different colors, that is full color and the pseudo color that are used for image processing. Similarly, we have the founder, how this came into existence, and it started from Isaac Newton when he passed white light through an optical prism, and the white light was dispersed into different colors. This was due to the different wavelength of the colors as they pass through the prism. So we talked of the electromagnetic spectrum, where we have low frequency as well as the high. Next, we have the quantities of light. So that is, we have the achromatic, we have the radiance, luminous, as well as the brightness. Next, we have the absorption of light. The absorption of light can be divided into different colors depending on their wavelength. Then next, we have the color fundamentals, where we have cones of the eye. Cones of the eye have the size of 6 to 7 million, and each color has a different percentage of which is absorbed by the cones. So 65% the color is red color is absorbed by the cones, 33% is absorbed by the cones, and 22% of blue light is absorbed by the cones. That means blue is the most sensitive, that is why it has a lesser percentage. We talked of the color formation. We have two types of colors. We have the additive and the subtractive primaries. In that case, we've seen these two color channels. I've shown you how we can be able to create them. Next, we have talked of color separation, and in separation, 3 parameters come into discussion. That is brightness, hue, and saturation. So for hue and saturation, all together they are referred to as chromaticity. And for that case, we can create a tri-stimulus that is decided by the International Standardization of Illumination, and that is now referred to as the trichromatic coefficients, and the total of these coefficients given by 1. Next, we've looked at the color fundamentals, and the color fundamentals have the purest colors along the edges. This diagram, that is, at this point you have pure green, at this point you have pure blue, and at this point you have purest red. Then we have the color fundamentals. So this is a summary of what we have covered so far and what we have discussed. So this is just a summary of it. And the saturation at point where there is equal energy, normally it's equal. So this is the color gamut that is used for different devices. The color gamut for RGB monitors uses additive color, while the gamut for high quality colors that is used, say, for printing devices, uses both additive and subtractive color. So this lecture has been prepared using the book Gonzalez and Woods, and the title of the book is Digital Image Processing, 4th edition, Pearson Publishers, year 2004. Now we're going to attempt the quiz together, and I'll guide you on how to respond to them. So the first question is, state the major categories of color fundamental. So the major categories, we have two. So we have the full color fundamental and we have the color fundamentals. Next question is, name any three low frequency bands. So any three frequency band, in this case is so here we are going to look at the following the second question, that is, name any two low frequency bands. So any three frequency bands are: one, we have the visible light, we have the radio, and we have the ultraviolet. So these are the three low frequency bands. The high frequency, we have the X-ray and the gamma rays. The next question is, differentiate between radiance and brightness. So I request you to go back, first understand what is brightness and radiance, and then you come back to this. Then discuss briefly on absorption of light. So definitely this one we've covered, and I'd like you also to go back and read on what we have discussed. Then discuss on color formation. So we said how colors are formed, and we've given the example of the glass prism and how they are formed different electromagnetic. So define hue, just you have to go back and define, but in simple terms, this is what is visible to the observer as either red, green, or blue. Then define saturation. Seen this. Compare brightness, hue, and saturation. All of these terminologies are straightforward and fast. And then what is color gamut? So we've given also this with the example of where it is applicable for RGB monitors as well as for printing devices. And we've said what is chromaticity. We've given what it is. When you combine hue and saturation, then you come up with chromaticity. So please go back, study this, and get a proper understanding. Everything is given. If you have any doubt, the resource reference book used to prepare this lecture is given. You can find more additional content which will be useful to you. Up to there, this is the end of this lecture, and I believe that it has been informative to you. And now I'm winding up till we meet again.